Hello, everyone, and welcome to the Department of Energy's SBIR STTR FY24 Phase 1 Release 1 Topics webinar. My name is Zina Al Yusuf. I am with the DOE SBIR Programs Office, and I will moderate today's webinar and provide you with some basic topic information as it relates to Release 1. Following this introduction, you will hear from the topic managers that oversee topics 26 through 36 as they clarify their expectations and answer some questions that you may have regarding their respective subtopics. During this webinar, you may submit topics-related questions via the Q&A box located in the bottom of your screen. We will group and present these to the topic managers following each topic presentation. Please include the topic and subtopic number with your question. This is very important to help us keep track of the questions. So please include the topic and the subtopic number. If you have a funding opportunity announcement or an other non-topic related question, please save these questions for the Phase 1 Release 1 Funding Opportunity Announcement webinar scheduled for Friday, August 11. Finally, a copy of the presentation and the recording of the webinar will be posted on our website, the SBIR STTR website, under the Funding Opportunities webpage. The program presenting today are Office of High Energy Physics and Office of Nuclear Physics. This is the third and the last webinar that will cover the Phase 1 Release 1 topics. There are 6 programs participating in this release, and we have about 103 subtopics. Today, we will cover the 2 programs we mentioned earlier. As you can see, the topics document was issued on July 10, and this week we are hosting the third webinar. We did have the on July 18 and 19, we have 2 webinars, and this is the third and final webinar today. The recording and the slides for both July 18 and 19 webinars are on our website under the Funding Opportunities webpage. The funding opportunities usually released 3 to 4 weeks after our topics are issued. We do this to give you the opportunity to read the topics and ask questions so you can make a more informed decision as to whether or not you might have something that is responsive to what we are looking for in this release. The most important date following the opening of the funding opportunity is the letter of intent due date, which is the first step you need to take in order to submit a full application. DOE is the only federal agency that requires a letter of intent. It tells us who you are, what topic, subtopic you are interested in applying for, and a little bit about why you think you are responsive for that subtopic. So basically, if you do not submit that letter of intent, then you cannot submit a full application to the funding opportunity. As mentioned, we have 6 programs participating in this release. We covered topic 1 through 15 and 16 through 28 last week. Today, we will wrap up with the topics from the 2 programs we mentioned earlier. The funding opportunity announcement is scheduled to be issued August 7. After that, we will have the funding opportunity webinar on August 11. In this webinar, you will hear from the SBIR STTR Outreach Manager, Dr. Eileen Chand, as she provides an overview of the application process and go over a few changes to the program. So you will want to register for that free webinar. It is also an opportunity for you to ask questions as it relates to the actual application process. However, today we are going to discuss the topics in just a little more insight than what is provided in the topics document. Please remember to join the mailing list if you haven't done so already, so you can receive our notification when topics are released, webinar registration, and some good information applicable to each cycle as we move through the phase 1 process. Please note that we use GovDelivery, which is a news application platform to send emails and notification. Please work with your IT group to allow you to receive these information. DOE Phase 0 Assistant Program is now open to all first-time DOE applicants. So if you have never applied to DOE before and looking for application assistance, I encourage you to go online. You can now find the link here or go to our website under Applicant Resources page and click on the link that will take you to the Phase 0 website, where you can complete a 3-minute application to see whether or not you are qualified for that service. It is a first come, first serve service, but it is something that can help you go through the application process. So what's a topic look like? Here's an example topic for you. We always have a topic header. That is the blue bar you see below the topic title and above the description. And it gives you important information like if the topic accepts STTR, yes or no, and the maximum award amount for that topic. Not all topics have the same information. They vary by program and by topic as well. So please pay attention to such information. The general topic description explains what the topic is about and maybe some context on where it falls within the mission of the program. Below that, you'll see subtopics that describe specific opportunities in which proposals are requested. You will notice that a good number of the topics have other subtopic. Under this subtopic, you can submit proposals that fall within the general topic description, but do not fit with any of the other subtopics. After each subtopic, there is question dash contact, then the name and email address of the point of contact that you can reach out to with your questions. Please note that every SBIR or STTR application must include the topic and the subtopic to which you are applying for. That's just a brief overview. And now we will start with topic 26. Darren?
Yes, I'm here. Can you hear me?
Yes, go ahead, please.
Okay, so topic 26 is about the advanced accelerator concept and the technology. As we all know, within the current technology, without significant advancement, accelerators and colliders are becoming more and more expensive, and the size becoming larger and larger. So we're looking for topics which can help to advance the accelerator technology and the physics. So the first one is a graphic user interface for accelerator modeling. For this particular one, we're looking for more user-friendly, intuitive interface to allow physicists to do more sophisticated modeling of accelerators from end-to-end simulations. We have programs which can do each individual component by pieces. We really like to see an integrate user interface allow us to do these simulations more effectively. That's what we're looking for. Okay. Another topic is a digital twin for HEP accelerator beam test facilities. We like to seek to build a digital twin for existing accelerator and the test facilities, allow us to explore new ideas and design experiments. More importantly, maybe can help us with these advanced AI machine learning controls. And for this particular one, of course, we need to work closely with National Labs accelerator facilities. The third one is non-destructive electron beam position monitors. This is related to the more advanced accelerator, laser plasma, weak field beam-driven plasma accelerators, which generate very, very short electron bunches at the femtosecond level, and with different, very difficult environments. We are looking for applicants who can help us to diagnostic and measure these beam properties more effectively. Any questions?
There is one question, but it's
okay. Oh, it's on the chat. Okay.
And the Q&A, yes.
Okay, let me see. It's a long.
Yeah, it's very long.
Where can the data of the top can be found? Interesting question. Where can the data? I do not know where can. Okay. What data you're talking about? Oh, you mean this beam parameters? I think we're talking about the beam facilities R&D like a FastNet 2 on the Berkeley Bella. You can find from the Slack and the Berkeley website.
He's saying that it's electron beam.
Electron beam, yeah, that's right.
Okay.
Yeah, FastNet 2 at the Slack and Bella at the Berkeley lab. Okay.
I guess that's it. I don't see other questions.
Thank you.
Thank you so much. Yeah, no more questions, so we can move to the next topic. Thank you, Darren. Topic 27.
Hi, shall I begin?
Please go ahead.
Okay. My name is Christine Clark. I'm speaking on behalf of Eric Colby, and I'm going to just discuss point A, and that's the low-cost radio frequency power sources for accelerator applications. We're interested in development of RF sources, both vacuum tubes and solid-state devices are included in this. As a high-level summary of what we're interested in low-cost, efficient sources for both warm and cold accelerators. Additional elements compared to last year is a bit of an emphasis on a couple of new ideas and concepts, which is a a short pulse moderate bandwidth C or X band klystron, and also solid state narrow bandwidth amplifier. Besides those two additions, it's actually very similar to last year's topic with a bit of rewriting. So since there's a variety of applications of RF sources and accelerators, we've tried to give lots of helpful references, which we do advise you to read to show what these are. We advise looking at these references to see how these RF devices that we're interested in are being used in the field and who the potential customers and R&D partners are. In terms of what are our key metrics, affordability is a really important metric for us. And when I talk about affordability, I mean the initial capital cost of the device and the device lifetime and also its efficiency. So operational lifetime costs as well. We are basically looking for a demonstration of devices that meet the output power and efficiency requirements and a clear path in the response to how the capital cost metric will also be met when the device is produced in volume. And if you look in the topic, you'll see the efficiency percentage and the dollar per average watt figures are stated for each application that we're looking at. Another common metric that we're looking at is stable locking. It's a requirement common across all of the RF sources we're interested in. Again, the figure to meet is given in the topic. And finally, in terms of frequency, we're interested in UHF and L band for continuous wave CW applications. And we're also interested in L band through to X band for pulse accelerators. And we'd like to invite applicants to pick where they'd like to respond based on where they perceive a market. Thank you. I see questions.
Just 1 second. I'm typing for a comment. It's for topic. I don't. Can you see it in the Q&A box?
I see a question that was about 26. So the one that Darren just mentioned. It's not really a question, I think.
Yeah, it's actually, can you, whoever typed the question, please include the topic and subtopic and your questions, just make it clear, please. Okay, at this point, I don't see questions. So we can move to the next subtopic. Maybe at the end of, after you and Ken covered all the subtopics, we'll have more questions.
Thank you.
Thank you. Ken?
Okay, subtopic B is for new superconducting RF cavity designs. The cost of niobium superconducting RF cavities remains a challenge for us. So a key motivation for this topic is new designs and processing methods that enable cost reduction while maintaining high performance, namely that is high cavity Q factor and electric field gradient. And there is a push to higher beam currents for our accelerators. So we need cavity designs that can be more easily tuned to the operating frequency and remain stable at high beam currents. Other challenges that need to be addressed include designs that minimize multipacting and field emission and that reduce sensitivity to Lorentz force detuning. So subtopic C is for auxiliary components and instrumentation for superconducting RF cavities. So there is a strong push to higher performance, as we've just mentioned, that requires commensurate advances in the auxiliary systems, and that is the focus of this topic. So the need for higher power capacity often means the auxiliary components become very expensive. So a key need is for cost-effective components, such as those listed in the topic language, that are capable of sustaining higher powers, higher gradient, and higher Q factors than present state of the art. So I will just call to your attention a helpful resource is reference 1 in the topic language, which provides a current high energy physics roadmap for superconducting RF R&D in the United States. So that is what I have for subtopics B and C. I will mention that the other subtopic, we will consider responsive other letters of intent that are related to the 3 subtopics that we listed. This isn't wide open for all RF accelerator technology, but if there is an idea that's not covered in the specific subtopic language, but is related to it, please submit those ideas.
Thank you, Ken. I don't see any questions in the Q&A box, so we can move to the next topic. Topic 28.
All right, that's me. This is Camille Ginsberg, and I'm speaking on behalf of Eric Colby, who's the technical topic manager, but he couldn't make it today. For laser technology R&D for accelerators, I'm sure you're aware of the many areas in accelerator applications where lasers are absolutely critical. We're focused on 2 areas. The accelerator application of ultrafast lasers, and also looking for longer pulse lasers. So we have 3 topics that are shown here. The topic A for high energy and broadband components for fiber lasers and arrays. That's a fairly wide open area where we're looking for low cost subsystem level components, power combiners, power splitters, pump power splitters, and et cetera. And we want those to be made as monolithically as possible. If you look in the document, I won't quote it, but please take a look at the table that's on page 69 that has a list of essentially specifications that we're interested in looking at. For topic B, high damage threshold, large area spatial light monitors, modulators. We are looking for something that can survive high power lasers. And in the document, we've got the resolution, the pitch, and the fill factor that are specified. As far as as Ken said, we're really looking within this area, should be aligned with the topic and within that table on page 69 that we've quoted. If you have specific questions like, is this a good topic? Please do get in touch with us by email. Again, the tech topic manager is Eric Colby. And also, if you're looking for partners, the references do have some people that you could contact if you want to explore finding partners.
Thank you. I see 2 questions. Would low subsurface damage? I'm not understand what's the question is about.
If you're talking about something that can tolerate a high power environment, that would be of interest.
Okay, so, would low subsurface damage optics to be of interest?
Yes, I think that would be interesting. Again, if you would like to discuss your specific area, I would strongly encourage you to get in touch with Eric Colby by email. He would love to talk to you about your ideas.
Okay, thank you. That is all for this topic. I don't see any other questions. So we'll go to the next topic. Ken?
Yes, high field superconducting magnet technology. The overarching motivation for this topic is to push to the highest possible magnetic fields for charged particle beam steering and focusing. There are, of course, other applications for highest fields, including NMR spectroscopy and laboratory magnets, MRI imaging. So there are more commercial applications for this technology than just high energy accelerators. So subtopic A, high field, high temperature superconductor wire and cable technologies for magnets. This subtopic aims to push the wire and cable technologies to higher performance at high fields and lower cost. We are not asking for basic material science, but development of technology for real HTS magnet conductors. So please pay close attention to the links and the critical current density metrics that are contained in the topic language. So we would expect a phase 2 award in this category to result in prototype lengths of magnet conductor, which could be tested in an R&D scale magnet. So for your information, the R&D partners are primarily the magnet development groups at our national labs, including Berkeley Lab, Fermi Lab, and Brookhaven National Lab. So reach out to me if you need contact information for the magnet technologists that are working in this area. Subtopic B is superconducting magnet technology. So we're mostly interested in innovations to push a high field boundary in these magnets using a hybrid high temperature superconductor, low temperature superconductor technology. And we're interested, again, both for dipoles and solenoid magnets. So a separate piece of this is most superconducting magnets that we use, including our accelerator magnets, have built-in sensors for temperature, strain, and in some cases, acoustic information. So there is a forefront topic at this time in cold electronics that enables data acquisition and processing in the cryogenic environment. So innovations in this area are part of this subtopic. So we would expect a phase 2 effort to result in a working demonstration magnet on a scale appropriate to the budget for an SBIR or STTR project that shows the advantages of the innovation proposed. So again, our R&D partners are primarily Fermi Lab, Berkeley Lab, Brookhaven. Reach out to me if you need contact information in any of these specific areas. So subtopic C. I did not think we had a C in this year's topics, but if there is, this looks like last year's subtopic. Maybe it did creep in. I'd have to look again. We are interested in cryogenic power electronics. So this is a different piece of the cryogenic electronics, and that is actually distributed powering and quench protection of the HTS and hybrid magnets that we're interested in. But please double check to make sure that is in this year's topic. So, and again, the other, we would want to see other ideas that are related to the specific subtopics. So that's it for 29.
Thank you. I will double check, Ken, regarding subtopic.
Looks like Michelle just looked and she confirms that that's subtopic C is in there.
Okay. Thank you so much. We have a question for subtopic A. Is it only for material developing or coating on tapes as well in phase 1?
It is for conductor development. So if your coating process is aimed at a magnet conductor and can produce links, and you show a path to the performance that we list in the table of metrics in the topic, then yes, we're interested.
Thank you so much. I don't see other questions. So we can move for the next topic. Thank you, Ken. Topic 30. Helmut, are you online?
I am. Can you hear me all right?
Yes, go ahead.
All right. So subtopic A, radiation hard sensors and engineered substrates. At our collider experiments, we make heavy use of silicon detectors for particle tracking and vertexing, and also for calorimetry. And currently, we mostly employ a hybrid technology where a separately fabricated sensor, silicon typically today, is bump bonded to a CMOS readout chip. Now, as we employ larger and larger area detectors, we're looking for new technologies to improve cost effectiveness of this, and we're looking for new concepts. A few examples, what we're looking for are monolithic CMOS-based detectors, that is where the sensor and the ASIC is all done in CMOS process. Another variation we're looking for are silicon sensors with moderate gain between, say, 10 and 100, but that are very fast. Fast here meaning 10 or so picosecond time resolution. Last but not least, we're looking to replace the silicon in the sensor with different materials. We're particularly interested in silicon carbide here, but we're also looking at other possibilities like diamond for particular applications. Now, for all of these sensors, radiation hardness is a very big deal for us. We have very high radiation environments, often reaching into the hundreds, if not thousands of megarats. Okay, so this is much, much higher than what you may be used to from the commercial environment. But this is something that we need to address in our technology development. Moving on to subtopic B, high density interconnects and integration. As I mentioned already, today we often use bump bonding to connect the sensors to the ASIC. We're looking for all ways to improve that. So we're looking for new technologies to make very high density interconnects with pitch less than 25 microns or less. We're looking at all kinds of ways to integrate. That is 3D integration, maybe with vias, or we're open to all kinds of ideas here. For any of these solutions, we have to retain our requirements in terms of maintaining extremely good timing resolution, extremely good position resolution, and radiation hardness. And last but not least, we're interested in integration of heterogeneous materials. That is, for example, non-silicon materials, nanomaterials, what have you, on top of CMOS. Subtopic C, electronics and sensors for ultra-low temperature experiments. Many of our rare event search experiments operate in the deep cryogenic environment, that is 4 Kelvin and below, sometimes down to the tens of millikelvin range. And we're looking for all technologies that are required to set up the whole chain from the sensor, that these could be transition edge sensors or kinetic inductance sensors or qubits, through amplification, through digitization, and then transmission all the way up to room temperature where additional electronics sits. We're also interested in all kinds of microfabrication, of superconducting, flexible interconnects all the components that are needed to set up this whole readout chain. That's it for this topic.
There is one question. Will you consider silicon carbide SiC bare substrate development to reduce the cost of manufacturing that do not include epitaxial growth or bonding?
So typically we don't use silicon carbide just as a bare substrate. We want to develop sensors out of silicon carbide. There are some details given in the topics language as to, for example, what kind of dopings and so on we want for the materials.
Thank you. I don't see any more questions. Oh, there's another one just came in. What is the minimal SNR expected end-to-end for 30C?
So that's not easy to answer. That really depends very much on the application. We would have to talk in detail about that.
Okay, so for this question, the person can send an email
Yes, sure.
Helmut. The email address is included in the topics document as well as in the presentation on the screen. Please contact the topic manager to further discuss. Thank you. No further questions for topic 30. We'll move to the next topic. Also, Helmut, go ahead.
So this is about high energy physics detectors. Subtopic A deals with photodetectors. Photodetectors are ubiquitous in all of our experiments, and we're looking for ways to improve over the traditional photomultiplier tube that has been in use for many decades. Now we're looking for photodetectors that that operate in particular wavelength regions that are fast, radiation hard, can be put into magnetic fields, and of course have high quantum efficiency. In some applications, these photodetectors need to operate in a cryogenic liquid, say liquid argon or liquid xenon. Sometimes they need to be built with low radioactivity materials to be deployed in experiments that search for rare events. In almost all cases, the experiments need large area coverage, so low cost is an issue. And if the photodetector is deployed within a cryogenic liquid, for example, it becomes inaccessible for an extended period of time, and thus it has to have high reliability. We're particularly interested in SPAD arrays that can be tiled such that you can cover large areas. And I should mention that we're always interested in fast, in particular for collider experiments, where fast here means that we need to get to time resolutions in the 10-ish or so picosecond range. I already mentioned radiation hardness. Depending on what the application is, that will determine what wavelength we're interested in. For applications that involve the cryogenic environment, we're typically looking at or interested in wavelengths below 200 or so nanometers. For other applications at collider experiments, we're interested in longer wavelengths. We're interested in a variety of technologies here. I already mentioned SPAD arrays or SIPMs. We're also interested in microchannel plate-based systems, as long as they can be highly pixelated and can be fast. Moving on to subtopic B, scintillating detector materials. So these are used in our calorimeter applications, in particular at accelerator experiments. And here we're looking for radiation hard, tens of megarad, fast, tens of nanoseconds, bright, something like 100,000 or more photons per MeV, and high density, something larger than, say, 6 grams per cubic centimeter. And last but not least, we're looking for cost effectiveness, because in some of the applications we have to cover large volumes, meaning multiple cubic meters. Okay. Traditionally in the past, we have used scintillating crystals for many of these applications. This topic is, for this particular subtopic, crystals are actually not within the scope. For this particular subtopic, we're looking for ceramic materials or for high-density glass. And then moving on to subtopic C, low radioactivity integration solutions. So I already mentioned in connection with one of the previous subtopics that some of our applications are experiments searching for very rare events. And for these experiments, radioactive backgrounds are problematic. And so we're looking for very high radio purity components for these experiments. And the most concerning contaminants that we need to reduce are potassium-40, thorium-232, and uranium-238. And so we're looking for components, including, for example, interconnect boards, that is printed circuit boards, or coax cables, or any kind of other cables that we can use in those rare event search experiments that have very, very low radioactivity. We're looking for something less than 100 microbecquerel per kilogram. And I think that's it for this topic.
Thank you. There is one question. Should it be for one? It's for subtopic A.
Yes, for the photodetectors. No, typically a particular application would focus on a particular area within the spectrum. As I say, if you're dealing with noble liquids, you would be looking at wavelengths below 200 nanometers. For sensors that read out scintillating materials, you would be looking more in the optical for applications in cosmology, you would be looking more at the red or the IR. So this broad range that's given in the topics language doesn't need to be satisfied in any single application. It is just that the range of our applications covers this whole wavelength range.
Thank you, Helmut. There are no more questions, so we can move to the next topic. 32.
Okay. This is a new topic. The technical topic manager is actually Eric Church, but he had a conflict today, so I will attempt to to substitute for him and tell you what he's looking for. So this is new. We had an AI ML topic last year, but it was focused on accelerator modeling and accelerator controls. This year, we're focusing on data for high energy physics. The motivation is to develop tools that enable high energy physics researchers to more rapidly develop and study machine learning models. So HEP has unique technical challenges that impact the development of AI ML applications, and we seek development of software tools that address those challenges for a broad class of HEP data problems. So data sets used for training that might naturally be on the scale of terabytes or petabytes are frequently reduced to gigabytes or smaller for convenience. But in doing this, information is lost or not properly captured. So similarly, changing the conditions or the apparatus requires researchers to train multiple models for each generation of a facility's evolution and for all possible conditions that may affect elements of the facility's performance. So the HEP scientific paradigm is to compare simulated data predictions with actual experimental data observations, and then make use of visualization tools to aid the process of drawing scientific conclusions. Integrating such visualization with AI ML software allows HEP scientists to gain insight into the machine learning network under study for a better physical interpretation of not just the extracted physics, but also of the network and its performance. Furthermore, the visualization of uncertainties in data sets is essential in drawing scientifically valid conclusions. So we expect pre-proposals to demonstrate relevance to technical challenges of more than one HEP subprogram or experiment and include specific HEP software that the development will interface to. Pre-applications that fail to do so will be deemed non-compliant. So that's the general background on this topic, specifically 32A, high energy physics, artificial intelligence, machine learning training tools, development of software for training on petabyte scale data sets or continuous lifelong learning. Facilitating large data set training can be accomplished by any relevant technique such as real-time, distributed, or asynchronous training. Applications for continuous learning should be able to handle data source evolution either through time-varying changes to measurement devices or their sensitivity to environmental conditions. So solutions addressing either challenge can be developed for homogeneous or heterogeneous computing architectures as appropriate. And topic 32B, AI/ML visualization tools. Development of software tools to improve visualization of scientific information natively integrated with both AI/ML and HEP software libraries. So applications submitted to this topic should focus on the ability to generate scientific publication quality plots of widely varying types of data and their associated uncertainties using a straightforward user interface, or developing visualization techniques to identify and display anomalous outcomes when comparing to reference data. So see the FOA specifically for more information, and with questions, please contact Eric Church because this is his area of expertise and not mine. So that's it.
Thank you, Ken. Thank you for covering for, oh yeah, we see that how to find national lab people genuinely interested to use and collaborate for the development of technology for topic 32.
Yes, there's a growing number of people at the labs that are interested. Please contact Eric to put you in touch with appropriate people.
Okay, thank you. For all questions regarding regarding topic 32, please, and I see another question in the Q&A box. Please contact Eric Church at the email address mentioned in the topic document, as well as here on, and we have it on the slides. Direct all your questions via email to Eric Church, please. Thank you. We'll move to the next topic. Topic 33, Michelle.
Yes, ma'am.
Hello,
Hi.
your time, so go ahead.
All right. Hi, everyone. I'm Michelle Shin. I'm Technical Topic Manager for the Nuclear Physics SBIR STTR program. I also have with me folks that function much like TTMs. There's Dr. Manusha Farkhande, who is the Topic Associate for Electronics. He also serves in the role of the SBIR STTR, what's called a portfolio manager. And then I also have the Topic Associate for Instrumentation, Dr. Elizabeth Bartosh, with me. And I'm going to sort of walk through these, but for the appropriate people, I'll ask my TA colleagues if they have any other words to say. So before I launch into exactly into the subtopic, I have a few general comments. Firstly, hopefully you folks have been looking through the overview for nuclear physics, but I really want to point out that we do not do anything in the energy area. That's covered by nuclear energy. And nor do we do anything in nuclear weapons. That's covered over in NNSA. All of these topics support nuclear physics subprograms. Our topic revision is based on our nuclear physics community's input. We have the goal that their input is based on their needs, projected needs, some 5 to 7 years out. And SBIR, STTR can't handle something that they need right now. You need your 3 years. Sometimes you can do faster than that, but that's where it is. Proposals have to demonstrate knowledge of prior art as well as the state of the art in any of the topic areas. It needs to be very innovative and of value to the nuclear physics community. Otherwise, it will not pass review. Also, very strong thing that we've had now for pushing, 7 or 8 years, is they must clearly indicate how the phase 1 R&D will result in a working prototype or method ready for testing by the end of phase 2. The prototype or method has to be suitable for testing in a nuclear physics application and/or at a nuclear physics facility. The language varies a little bit for software, this particular one, topic 33, and I just will refer you to that document. So moving on more specifically to that particular software and data management, the experiments that we have, particularly in our flagship facilities, CBAF at Thomas Jefferson National Accelerator Facility, also it's called JLab or Jefferson Lab, and the rare relativistic heavy ion collider at Brookhaven National Laboratory annually produce 50 to 100 petabytes of raw data. And the reduced data sets that are then sent out to researchers are of order many hundreds of gigabytes up to a couple of beyond terabytes. In the future, the facility at Rare Isotope Beams in Michigan State and the electron ion collider cited at Brookhaven National Lab will be producing similar amounts of data. So we make requests in the following subtopics. We have tools for large-scale, widely distributed nuclear physics data processing. So we're really looking there for effective movement of data. And that's the storage, retrieving large data sets at lower cost. Really on the moving That's all being really done on the DOE's ESNet. We're not interested in you trying to reproduce ESNet. But you would want to be familiar with the ESNet and how you can best have the researchers at academic institutions and our national lab facilities use that or move that data. And again, as you might guess, it's our community is the primary user of all of this. You can contact me or Gulshan Ray, and we can help you put you in touch with the appropriate people. The next subtopic is application of emerging data science techniques to nuclear physics. So as you can imagine, AI and machine learning have been used actually in nuclear physics for decades. So what we're hoping for here, what we're anticipating, not hoping, what we're anticipating, what you've got to do is go beyond saying, well, we're going to use graphical neural nets or something like that, to analyze nuclear physics data. No, you can't. That's not going to fly. We already know how to do that. What we need is that you need to go look at the references that are provided or in topic 36 instrumentation and see where can you make a play that could be helpful to the community. And you'll need to be, it's really important you need to make a connection. You can't just say, we're going to help the nuclear physics community. No, you need to say, gee, we're going to work with the medium energy community at Jefferson Lab or such. And so again, we can help point you to appropriate places, but you need to really tell us, that you're up to date with what our community particulars are doing, and that you can do something innovative and go beyond what they could do. Again, looking at a time horizon of sort of 5-ish years. And then lastly, heterogeneous concurrent computing. So we already have high performance or what are called leadership class facilities, and these are stewarded by the Advanced Scientific Computing Research OSCAR office, also in this release. And so what we're looking for is that so often tools that are used to analyze data are often written by, say, a professor and their graduate students or postdocs. And there's a lot of latency built into some of this. And it would be good if someone who's really a domain expert could go in and make this code run faster on our leadership class facilities, or even the high performance computing facilities scattered, at the national labs that we've got, or at universities. And again, in all points, you've got to, it's in the topic, connection to a particular community, an instrument, say class 12 at Jefferson Lab, S Phoenix at Brookhaven, Greta at Lawrence Berkeley National Lab, or in a particular nuclear physics facility, like I just pointed out. And then, of course, we have other. Let's see, Zena, I see 2 items in chat.
Yeah, and the questions are 30. What size scale of prototype would you expect at the end of phase 1, phase 2? For example, tens of heterogeneous nodes, 100 of nodes, etc.
Well, that's a good question. One of the nice things, again, if you go look into the topic, James, is that you can request cycles on NERSC at Berkeley Lab. So obviously you can't ask for the moon, but I would think certainly 10 to 100 nodes for some periods of time would be fine. What would probably be best, though, is to connect with a group and then get permission to be a user on their cluster and run it and then they'll help you define the nodes. So there's that one. Let's see. And again, in C, what would be the best way for an applicant to identify well? So I've given you references right up there at the top on the yellow report, which has a list of authors and their institutions. And that would be a great start. I can help you, or Gulshan can, with the appropriate people for any of these larger experiments. And for the what's called the EPIC collaboration, which is designing the detector for the electron ion collider.
Okay, and now we have one more question. What is the threshold to be considered innovation? Is it passing the patentability threshold, or something more or less?
Yeah, that's a good one. Patentability would be a great threshold to set, but I think that's a pretty high bar. It doesn't need to be that high a bar. In this area, it's, you know, we recognize what I call the swing of the meter. We will know what passes on innovation. What you've really got to do is say, is if you have a particular area, say in data science technique for helping our folks with the analysis of their data, being able to put together an event, you'll have to talk with them. And if they say, oh, that's really cool, and yeah, we would like to write you a letter of support and such as that, then that's a good indication that it's innovative. If it's, well, we're already doing it, then it's not. So hopefully that helps answer that question.
Thank you so much. No further questions, so we can move to the next topic.
Okie dokie.
It's also you, so go ahead.
All righty. Listed on there is my friend and colleague, Dr. Manusha Fakande. In nuclear physics design and fabrication, what we're really doing there is you've got an instrument, and some of these things are quite large. They fill buildings or a building size. Some are much smaller. They can fit in a room. But in all points, we're looking for finer resolution. In other words, more effective number of bits, increased number of inputs, faster sampling rates, all at a lower power consumption and cost per channel. So you can go through and look. We have a lot of specs in this topic now. I will say that many of them are for specs that are for our facilities that need very high data rates, again, like Jefferson Lab or at Brookhaven. But next generation, in general, next generation nuclear physics instruments need 16 bits effective number at sampling rates and channels, and 64 channels minimum. I could go in, but the subtopic has the specs that you really need in that area. For nuclear structure, nuclear astrophysics facilities, where the data rate comes in slower, like at Atlas, at Argonne, or at TAMU, or at, the Cyclotron Institute facility at Texas A&M, places like that, they don't need quite that kind of data rate, but this is where we're trying to push the state of the art. So really looking to those communities, heavy ions and medium energy would be the way to go. That's subtopic A. And subtopic B, front-end application, front-end ASICs. Front-end means that these are the detectors that are bolted right up against the sensor. So they are sitting closest to interaction points, whether they be a fixed target, say at Jefferson Lab, or if it's an interaction region at a collider like RIC, or again, eventually the EIC. So they need to be radiation resistant, and relative to the state of the art, the microelectronics should be user-friendly to program and capable of communicating with commercial auxiliary electronics, and the specs are all in the subtopic. Then finally, in subtopic C, are next generation pixel sensors. So, for the greatest extent, the sine qua non is the MAPS sensor, and the CMOS, somewhat akin to what you can get in a camera. What we're looking for are smaller, meaning more pixelated and more radiation resistant active pixel sensors. This is really going to be needed in the EIC, the electron ion collider era. We're asking for options to explore would include interconnections to give you 2.5 and 3D architectures, initial signal processing right there on the chip, on the sensor, possibly superconducting, large area detectors, more segmentation, as I mentioned, and things like that. It's all in the subtopic, and then of course we have other. I don't see any questions right away. I want to invite my friend and colleague Manusha Farkhande, if he has any other comments he might want to say. Oh, we've got a Q&A. But Manusha, do you have anything you want to say?
No, you covered everything, and if there are questions, we certainly will be happy to respond. This is the area that, the subtopic's been part of NP, and the same thing is similar to HEP for many years. We're just looking for essentially evolutions and just improvements. And as our experiments get essentially need essentially faster timings and more channels. So you covered everything. Thank you.
Yeah, you're welcome, Manusha. And there you get to hear his voice and see his face. I think the best way to communicate with us is email. A lot of folks want to get on the phone, but it's tough with everything else we're juggling. But by all means, send us emails. Now let's see. Michael would it be okay?
Michelle,
Sorry.
I see two questions for data acquisition system. What bandwidth and data rates?
Well, that's actually listed in the subtopic. We're looking at sampling rates for those 16 effective number of bits. We're looking at sampling rates greater than 4 gigahertz at a bandwidth greater than 2 gigahertz.
Would you be okay with overlap in quantum computing in some of this work?
The short answer is you can mention it on the side, but that is not what this topic is about at all. And if you try to make that the focus, then we would reject it as not responsive. I mean, if you could say, well, there might be something that can be, this could be, it's okay to have a one-line sentence, but that is not, the community that's asking for this is not, they're not doing quantum computing or attempting to do it. They're looking for they're looking for hardware that goes in a rack in 3 years that they can test and look forward to it being innovative to the point that they want to go off and buy a bunch of them from you. So hopefully that's your answer.
Thank you. I don't see more questions, so we can go to the next topic.
All righty, so that's nuclear physics technology, and I'm the topic associate for that. I have some 20 plus years in this area. With actual sitting in the control room, down on the floor, bolting beam pipe together cleanly, I might add, and that sort of thing. So we've got what we call 4 microscopes, and all of them are nuclear or accelerator facilities, and they're all listed in the beginning for the overview. So accelerator technology is a very important area, and you can see that it has more subtopics than the others, although Many of these subtopics have been pared down to just one ask. And that's because what we found over time is that the other asks are really looking for possible innovations, but the fact of the matter is everything works okay with what they've got. So it's better if you thought you had something, it's better to contact the facilities and say, is there anything you could build that we can build to print? So in the area of materials and components for radio frequency devices, you don't see things like new gate valves and new forward power couplers or windows for SRF cavities. What you see is new cleaning. The one item that we still would really like to see a solution for is new cleaning techniques to remove particulates, not hydrocarbons, but actual particulates from superconducting cavities, inner surfaces, while they are in situ. So we know how to clean them. If we pull a cryomodule, a superconducting unit, out of the tunnel, out of the accelerator vault, and we take it apart, and it's taken apart in an ultra high clean room and all that. That's a well-established procedure. Cleaning particulates in situ would be a game changer and quite innovative. And for it might be much easier to do for, say, quarter wave cavities than I can't. It's hard to imagine how you would do it in an elliptical, but that's what we're looking to you folks for. So the next one, subtopic B, is design and operation of RF beam acceleration systems. This again has become just one ask, and that is RF control systems for tuning and synchronization of multiple crab cavities. This is going to be needed in the electron ion collider. For particle beam sources and techniques, we have polarized electrons and polarized ions. In particular, the light ions can be very highly polarized, and that of course decreases, along with the atomic number as you get heavier. But nonetheless, we're looking for longer lived and better electron and ion sources. Also looking for quench protection, new quench protection systems for high temperature superconducting magnets and such, which will benefit our nuclear physics facilities. So as you can imagine, all four of them could benefit. When it comes to ion sources, that's not really of any importance to, as much importance certainly to Jefferson Lab, but they do have some low energy areas. But it would be very important for FRIB, for Atlas, for the 88-inch cyclotron, and a number of our facilities. Next up are polarized beam sources and polarimeters. If you're going to make a polarized beam, you want to be able to measure that level of polarization. And these beams are pretty darn intense. So it's not something that, if you could figure out how to do it without interacting with it, in other words, a non-intercepting system, that is what we're really looking for. And again, we're looking for longer lived polarized electron and ion sources. And within this, there are some caveats. For example, on the electron source, lots of people want to propose, we want to do cadmium telluride or something like that. Well, the community is pretty much set on for spin polarized electrons using gallium arsenide that's been strain layered with things like that. So we're very specific on what we're looking for in that area. And for non-polarized, which would be back to part of subtopic C, the bialkalis are doing very well. So it would be, improvements there. Let's see, we then move on to subtopic E, rare isotope beam production technology. There's some asks primarily from FRED because they make the most radiation. If they have an intercepting phase space, say diagnostic, they're looking for diagnostics near the production target. And so that's all listed, and the specs for what sort of radiation that they will be encountering is all in the subtopic. And that brings something and sort of touches, I think, Helmut or Ken mentioned it. The radiation doses are coming from very energetic neutrons and charged particles. Finding it would be good to try to figure out or to work within our communities to find a good way to test them, because, for example, if you're doing neutron doses, you just can't go to some university with a trigger reactor, and snuggle it up and, get a whole bunch of thermal neutrons. We really, it's more than just the mass of the neutron. It's the mass coupled with all that momentum when it comes in, at a very high energy. So keep that in mind, and I can, where we can help you, we will. Moving on, we get to the last subtopic with content, and that's control and diagnostics. So clearly, if you're doing electron beam diagnostics, they're not going to be the same as you're doing with different ion species. So we actually break out the requests by the community to what are we looking at? Are we looking at very high power, intense, heavy ions, or charged ions? Or are we doing electrons? Are we doing lower energy, down around the Coulomb barrier, 6 to 10, MeV per nucleon, like what's going on at the Cyclotron Institute at Texas A&M, or at Atlas at Argonne. So look at the specs. That's all there. And then of course there's other. Okay, questions. What is the timing, frequency, and phase synchronization precision required for operation and for diagnostic accelerators and the distance to cover? Okay, so, well, that's a great question. And that depends on what facility you want. I guess what you're going to have to do is contact me and, for what area you're interested in. And I can tell you. And I see that, okay, now we get to D. Can you comment on required efficiency? Well, yes. I guess I need to know efficiency for the electrons or efficiency for the ions. I'm going to guess for the electrons. That's listed. We're looking for quantum efficiencies of 10%. For ions, I'd have to refer you over to the subject matter experts at Berkeley or Argonne or Everett. So you'll just have to shoot me an email and I can get that for you.
Okay, I'm gonna type SPE 35 SPE.
I don't recognize that acronym. And 35 has got lots of, there's quite a few subtopics, so I need to know which subtopic are we talking about and what is SPE?
I just typed an answer to contact you via email.
Okay, thanks. Oh, the spin polarized efficiency. Oh, it needs to be, we're looking at 90%, 95%. It's all in the topic too, the subtopic.
Thank you.
You betcha. Okay, so we're working down to the end. Topic 36 is nuclear physics detection systems and techniques. And my friend and colleague Elizabeth Bartosh is online. I'll have her say a few words if she'd like after this. So you see both of our emails there. So our topic objectives are advanced detection systems, instrumentation, and techniques for nuclear physics experiments. I've already mentioned that these instrumentation, which are outfitted with electronics, either close in or you carry the information back to the control room, that these things can be fit in large rooms, or can be large multi-story buildings. I'll point out as a side note that historically, since I've been tracking this, products and methods, mainly products, from the instrumentation topic have had the highest rate of commercialization. So we have we've condensed this down to 3 subtopics plus other. The first one is advances in detector and spectrometer technology. What we're looking at, of course, are when you're looking at, say, the EPIC detector, or that'll go into the electron ion collider, or systems like Muller being built at Jefferson Lab. These large area, we need large area at lower cost detectors to detect, analyze, and track photons, charged and neutral particles. In many instruments, particularly at Jefferson Lab or at Brookhaven, they must be radiation resistant and magnetic field tolerant. There's a lot of specs in there for what are the radiation dose levels, what are we looking for the speed, or the data acquisition times and rates. So just see specs in the subtopic. Moving beyond sort of the large scale, and we listen, multi-well detectors and things. We're looking for development of novel gas and solid state detectors. So it's sort of an adjunct, and again, to what is in subtopic A. Again, look into the subtopic where we have all the requests and the specs. And the last subtopic, C, technology for rare decay and rare particle detection. A really strong emphasis in the department, in the office, excuse me, in our communities are fundamental symmetries. So trying to do things like look for a rare decay called neutrinoless double beta decay. We're looking for detectors and techniques to measure very weak or rare event signals. The technologies and analysis are required again for things like neutrinoless double beta decay, or for new isotopes that are produced far from stability at rare isotope beam facilities. To some extent, this would be Atlas at Argonne, but very much so FRIB at Michigan State. So, so those two are the main users of that. To some extent, it could be used probably at the 88-inch cyclotron at Berkeley Lab. So that's it. And then we have other. Elizabeth, do you have any further comment?
Well, I just wanted to say thank you for wrapping that up and stating it so well. I don't have anything to add because your emphasis was appropriate. I just want to say that I welcome any inquiries from the folks on the phone today.
Super. Thank you so very much, Elizabeth, and again to you, Manashir.
Thank you so much. No further questions. And by this, we come to the end of our webinar for today. As we mentioned at the beginning of this webinar, we will post the slides and the recording on our website under Funding Opportunities page. Here we have our contact information. Please feel free to reach out directly to Carl Hebron, who is the operation manager in our office. Carl and his team can answer just about any question you may have about the application process. And that will be it for today's webinar. And thank you for attending.